My name is Ania, and this is the first lecture in my course on battery management systems. I'd like the world to transition to sustainable energy, and presently, batteries are key. I've spent some 16 years working on battery management systems, from analog chip design through product definition and safety analysis. The world needs more engineers who know what I've learned. So, I'm creating this course. Thank you for joining me. In this first lecture, we'll talk about batteries, a prerequisite to managing them. We'll start with a quick review of rechargeable battery chemistries and energy density. Rechargeable batteries vary in energy density. In this plot, we see energy density increasing from lower left to upper right. The lead-acid battery, commonly used as the 12-volt battery in gasoline-powered cars and invented in 1859, has a relatively low energy density. NiCad and NiMH are both commonly sold as AA size batteries. Lithium-ion batteries dominate the electric car space, largely thanks to their high energy density. Lithium-ion is actually a family of chemistries. Two of the most common for electric vehicles are NCM, nickel cobalt manganese, and LFP, lithium iron phosphate. The F stands for Fe, the periodic table abbreviation for iron. Let's define energy density and discuss how it differs from power density. Energy density refers to how much energy is available for a given volume or mass of cells. This corresponds to how many hours an application will run at a constant power load. Power density refers to how much power is available per given volume or mass of cells. That corresponds to how many amps of instantaneous current the battery can provide. For a vehicle, the energy density determines the range, while the power density determines the acceleration. For example, for a Tesla Model 3 long-range battery, we can calculate the energy density from the battery capacity and weight, and calculate the power density from the vehicle's peak power and the battery weight. Note the different units: watt-hours per kilogram and watts per kilogram. When should we optimize power density versus energy density? Some cells are better at providing high peak power, some are better at storing a lot of energy, and some cells have other features for which we may wish to optimize while sacrificing either power or energy density. Pause the video for a moment to list a couple applications that should optimize for energy density and a couple for power density. We optimize for energy density in applications where current draw is fairly constant and we want the application to operate for a long time. Power density should be prioritized in applications where the current draw is expected to have large peaks. For example, energy density is important for long-range trucks because the current draw is fairly constant and they need to go for a long time. Power density is important in applications such as race cars, which need to accelerate quickly with correspondingly high peak currents, or RC helicopters, which have high peak currents but the duration of usage is low. If you're interested in comparing cell chemistries, this table is a nice reference, and you can pause the video to read it in detail. We'll see pieces of it in this lecture. A more detailed yet version is available at the link at the bottom of the slide. Next, we'll talk about the OCV versus SOC curve, which is key to characterizing and managing a lithium-ion battery. You can't talk lithium-ion batteries without the OCV versus SOC curve. On this plot, the y-axis is cell voltage, and specifically the cell's open circuit voltage, which means no current is flowing, and no current has been flowing for some rest period, perhaps a few hours. The x-axis is the state of charge, or in other words, how many % full the battery is. Charging the battery moves up this curve, and discharging moves down the curve. The cell manufacturer specifies what voltage corresponds to 0% state of charge and to 100% state of charge. 2.7 volts and 4.2 volts are typical for NMC cells. The shape of the OCV versus SOC curve is slightly different for every cell chemistry. Notice that the LFP curve is very flat in the middle. This poses challenges for using cell voltage to monitor the state of charge of an LFP battery. For an NMC or NCA cell, the battery management system can measure the voltage to deduce the state of charge. For an LFP cell, the flatness of the curve requires very precise voltage measurements. We'll consider this more in the lecture on the value of accuracy. You may also see a related plot with the x-axis representing charge in amp hours instead of state of charge in percent. As a side note, the rigorous name for stored charge is residual discharge capacity. The state of charge is defined as the presently stored charge divided by the total cell capacity. If you know the cell's total capacity, you can readily translate between these two presentations of the same underlying data. Now, we'll dive into a slightly longer section on design for battery safety, including a couple case studies. Cell chemistries vary in how safe they are. Some chemistries, like lead acid, NiCad, and NiMH, are quite thermally stable. What thermally stable means is that if you damage or short-circuit one of these cells, the consequent local heating will not spread. It will not go into a positive feedback cycle leading to thermal runaway, exothermic behavior, fire. Lithium-ion chemistries, on the other hand, can go into thermal runaway. For example, a localized short can cause localized heating, which heats up adjacent areas and damages them, resulting in more shorts and more heat, and the self-heating propagates, a positive feedback cycle possibly resulting in fire. The chemistries most commonly used in electric cars are in this category and thus require careful management. Some lithium-ion chemistries are thermally stable, namely some lithium iron phosphate batteries. Many lithium-ion chemistries are not thermally stable and can go into thermal runaway. The causes of thermal runaway are overheating, or overcurrent causing overheating. Overcurrent can be due to a short inside the cell or due to a short outside the battery, such as after a crash. Overcharging can also cause thermal runaway. Something we can do for cells that require management is to have a battery management system, and that is my expertise and the focus of this course. A BMS can prevent overcharge by monitoring each cell's voltage and stopping charging when the voltage gets high enough. It can prevent over-discharge and consequent damage by stopping discharge when the voltage gets low enough. A BMS monitors temperature and will reduce operating power in the system or activate a heating or cooling system as needed. And it can stop overcurrent conditions due to external shorts by opening a contactor, which is basically a switch between a battery and the rest of whatever system the battery is powering. But what about internal shorts? What about internal shorts? We'll review battery construction, then a case study, and finally discuss 3 engineering solutions. These images show the various parts of a cell. Pouch cells, prismatic cells, and cylindrical cells all have an anode, a cathode, and a separator, and differ in the way that these layers are folded or rolled together. For this class, I need you to know that the anode and cathode are the 2 terminals. The separator is easy to remember because the separator separates the anode and cathode. Let's zoom in. This is what the cathode, separator, and anode look like in a scanning electron microscope photo. On this scale, we can see how porous the anode and cathode are. Filling the gaps is electrolyte. The electrolyte is the medium through which lithium ions flow on their way between the anode and the cathode. When we get to cell models, we'll talk about electrolyte impedance. As a side note, research is ongoing on solid electrolytes, which are appealing because a solid electrolyte cell is smaller, or in other words, has higher energy density. The challenge is that as a battery charges and discharges, it physically shrinks and expands, which is problematic for solid electrolytes. This is a topic of active research. Let's do one back-of-the-envelope calculation to gain some intuition into how much separator we have in a single car. Start with a web search. In a single Tesla battery cell, there's about 1 meter's length of jelly roll. So 1 meter of anode and 1 meter of cathode, with 2 meters of separator keeping them apart. A 2170 cell is 21 millimeters by 70 millimeters, thus the name. Now some math. The separator area in a single cell is about 1/6 of a meter squared. And another search. The long-range Model 3 has 4,416 cells. More math tells us that 4,416 cells contain just over 600 square meters of separator. What does that mean? I can't visualize 600 square meters, but I can visualize a swimming pool. So let's put that in terms of swimming pools. The separator in one long-range Model 3 has an area similar to half an Olympic swimming pool. Okay, that's intuition. One last search. Tesla sold nearly 1 million cars in 2021. In 1 year, Tesla's vehicles contained as much separator as the area of the city of Chicago, or Zion National Park, or 10 times the area of Manhattan. Can we expect such an area to be free of defects that might lead to internal shorts? What do you think? There are 2 correct answers. Chevy says yes, Tesla says no. Let's look at Chevy first. Chevy recalled the Bolt due to some exothermic events, fires, which Chevy explained as being caused by the simultaneous presence of 2 rare manufacturing defects, a torn anode tab and folded separators, in the same battery cell. The Chevy Bolt manufacturing defect meant that sometimes, in some cells, the cathode and the anode were not properly separated. Sometimes, in some cells, they would short, and that led to thermal runaway. Chevy's solution to the recall is to, quote, work aggressively with LG, their cell supplier, to adjust production to have replacement modules available as soon as possible. Chevy seems to expect that LG can manufacture cells well enough that internal defects can be mitigated by excellence in manufacturing. Tesla's approach includes safety through mechanical construction. On the left, you see a partly deconstructed Tesla battery pack, and below you see the text from a Tesla patent. LionSmart, a small engineering company in Europe, phrased the same idea more simply. Individually fused cells embedded in a fire-retardant medium. Individually fused means that each cylindrical cell is connected by wire that acts as a fuse. So in case of an external overcurrent condition, that wire will open like a fuse, and that cell will disconnect itself from the rest of the battery. Embedded in a fire-retardant medium means that if one cell goes exothermic, hopefully that fire-retardant medium will keep that exothermic event from propagating to the neighboring cells. In summary, let's review 3 approaches to safety. The most common approach among large car manufacturers is to use NMC cells susceptible to thermal runaway and count on excellence in cell manufacturing. This is true for the Chevy Bolt, as well as a number of other cars you may have heard of. A second solution is Tesla's solution to use cells susceptible to thermal runaway, but provide for safety through mechanical construction, limiting propagation of exothermic events. A third option is to use LFP cells, which do not go into thermal runaway, and accept their lower energy density. A number of companies have turned in this direction recently. In late 2021, Tesla announced the switch to LFP for standard range vehicles while continuing to use higher performance chemistries for their higher performance cars. Ford will be switching to LFP for their Mach-E and F-150 Lightning. Hyundai started developing for LFP in 2021. The list goes on. To manage batteries, we must understand how they behave, so we know which behaviors we must monitor and manage. We'll quickly review what can affect lithium-ion cell lifetime and go deeper in a later lecture on cell behaviors. In the next few slides, we'll look at some rules of thumb for lithium-ion batteries. Battery lifetime varies across cell chemistries. As we cycle cells, their capacity degrades. Generally, LFP cells can withstand more cycles than NCM or NCA. How the cells are used also affects their lifetime. Hot temperatures increase degradation. A cooling system or operation in moderate climates extends lifetime. Storage at high voltage or high state of charge decreases lifetime. Avoiding charging to full extends lifetime. We have an engineering trade-off between capacity and lifetime. If you charge to 90%, you get only 90% of the available capacity, but you get more cycles. High currents also reduce lifetime. We'll see a quick overview of these phenomena in the upcoming slides and go deeper yet in the future lecture on cell behaviors. These tables are from different sites but show the same message. LFP cells can withstand more charge-discharge cycles than many other lithium-ion chemistries. And lead-acid and NiMH have insufficient cycle life for most vehicle applications. Their energy density wasn't nearly as good as lithium-ion either. This plot is from a really nice publication showing calendar aging in lithium-ion cells. We'll look at this paper in more detail in the lecture on cell behaviors. The authors stored cells at a constant temperature for 10 months and measured their cells' capacity at the end. On the y-axis, we have that measured capacity. On the x-axis, we have the state of charge at which the cells were stored. Cells stored at lower state of charge degraded less than cells stored at high state of charge. The cells stored at higher temperatures degraded more quickly than those stored at lower temperature. Temperature accelerates capacity degradation. High currents also accelerate degradation. For example, this study varied the charge rate of NMC cells and assessed cycle life. A 2C charge rate caused mild degradation, while a 3C charge rate resulted in dramatically worse cycle life, and 4C caused catastrophic failure. We'll look at the study in more detail in the lecture on cell behaviors. We talked about capacity degradation due to aging. Also important is cell impedance increase with aging. With zero current flowing, the cell's internal voltage equals the terminal voltage. With a load current, the terminal voltage drops by an IR drop. The larger the internal impedance R0, the larger this drop. Whatever voltage is defined as the cell's minimum operating voltage, an aged cell will reach that voltage sooner than a new cell with a small R0. We either cannot discharge the aged cell as deeply or must reduce the current at the bottom of discharge. Let's return to those rules of thumb and discuss design mitigations. When choosing which cell to use, ask the manufacturer for their cycling data or collect your own to ensure that the cell is appropriate for your application. Specify an appropriate cooling system. Minimize charging to 100%. High currents also reduce lifetime. Be mindful when deciding whether to fast charge and how fast exactly and how often. In this section, we'll discuss charging. Before we dive into charge rate, though, I need to introduce a bit of terminology. In the context of batteries, C, or C rate, is used as a measure of a cell's current relative to its capacity. A 1C current, by definition, will discharge a battery in 1 hour. For example, for a battery with a 100 amp-hour capacity, 1C means a current of 100 amps. We will briefly mention 3 concepts around charge rate. We'll review the common CCCV charge profile, then temperature range for charging, and lastly, fast charging. Lithium-ion cells should not be overcharged. Overcharging damages lithium-ion cells. To address this, lithium-ion cells are typically charged with what's called CCCV, or constant current, constant voltage charging. From 0% state of charge to about 80% state of charge, the cells are charged with constant current. Once the cell voltage approaches the cell's maximum voltage, we switch to constant voltage charging, with the charger applying whatever voltage corresponds to 100%. During the constant voltage phase, the current tapers. Note that this results in a charge profile that charges slower near top of charge. In this figure, the first 80% of the capacity is charged in less than half the time. Batteries operate best within about 20 degrees C of room temperature. This is true for all cell chemistries, though you can see that lead-acid batteries outperform lithium-ion below freezing. Fortunately, lithium-ion batteries operate well at temperatures that are comfortable for people, which makes them sufficient for many applications. For operation in extreme climates, either below freezing or above about 45 C, either a heating system or a cooling system or both are necessary. Let's talk about fast charging. First, it's easier with cells optimized for high power density. Second, high currents can reduce lifetime, and whether that's a worthwhile trade-off depends on the application. Third, charging can be thermally limited. No chemical process is perfectly efficient, so charging generates heat. When the battery is already warm, the battery cooling system may be the limiting factor on charge rate. In cold climates, the battery may be too cold to fast charge upon arrival at the charger. In addition to implications for the battery itself, fast charging requires appropriate infrastructure outside the vehicle. For example, a typical home outlet can charge my car in about 40 hours. Charging from a 240-volt dryer outlet reduces that to less than 10 hours. A fast charger requires higher power infrastructure than is available at many homes and businesses. I've seen the internet mention a rule of thumb to avoid charging above 1C. That's not necessarily good enough for fast charging, and many lithium-ion chemistries can withstand far more. In summary, we looked at how the CCCV charge profile protects against overcharge, but results in slow charging near top of charge. Temperature matters. While detailed information on degradation as a function of current is tough to find on the open internet, it is essential to an optimized design. Good management of a lithium-ion battery typically requires a heating and cooling system, and operation with reduced power when the battery is hot or cold. Fast charging requires care, as summarized in the previous slide. The optimization of charge rate leads us to different solutions for different applications. For example, the 300-mile range of my Model 3 covers all my in-town driving. If it takes a few hours to recharge at night, that's just fine. We fast charge only on road trips every few weeks. A bus needing to operate 12 hours per day with multiple recharging stops per day is a very different story, an application where repeat fast charging may have much higher value. Calculating the overall system cost is a good way to make trade-offs across systems and across different parameters. I'd like to give you a glimpse of battery system architecture. A battery in an electric vehicle is one of the most complicated battery systems that you may encounter in daily life. A home energy storage system or a cell phone likely have simpler battery architectures. We'll go through this diagram slowly. Let's start with what the BMS, or Battery Management System, needs to do to keep cell voltages within their operating range. To prevent overcharge, the BMS needs to communicate with the charger. This is likely to happen via the vehicle CAN bus. Also, the BMS needs to communicate with the load, in this case, the motor, to indicate whether it may pull current and how much. The BMS also may need to communicate with the main vehicle computer. For example, my Tesla automatically turns off Sentry mode, which is the car alarm, when the battery reaches 20%. Cell temperatures are also an important BMS measurement, letting the BMS detect when the cells are too hot, too cold, or just right. To keep them in the just right range, the BMS communicates with the heating or cooling system. Let's also talk about what happens if something goes wrong. In case of some issues, the vehicle may notify the driver. For example, if the battery is very cold, the system may limit power, resulting in reduced acceleration, and the vehicle may issue a user notification. As another example, if we lose a cell voltage sense wire, we don't have an immediate safety issue, but it is unsafe to charge, and the vehicle may warn the driver to please head to a safe destination and call for service. For internet-connected or cell-connected applications, the system may issue an alert or send data back to the manufacturer. Some of that data or alerts may come from the BMS. The BMS also controls the contactors or battery switches. When a vehicle is inactive, the contactors are usually open. When the user turns the car on, the BMS should run some safety checks and confirm that all is well before closing the contactors. Some faults should result in the BMS opening the contactors or the fuse blowing open. An electric car also typically separates battery ground from vehicle ground. Any communications between the two ground domains must go through an isolated interface. Now, let's consider what would be simpler for a 50-volt stationary energy storage system. We don't need wheels. The charger connection might go to solar panels, and the charger gets replaced by a DC-DC converter between the battery's 50 volts and whatever the solar panel array outputs. We lose the motor and the motor controller, but the circuit to generate a home's 120 volts AC is actually in many ways similar to a motor controller. Importantly, since 50 volts is much safer than 400 volts, and since regulations reflect this, the high voltage isolation may go away or be much simplified. With that change, we also may lose the need for separate grounds. With shared grounds, we may not need the low-side contactor. We lose the car's 12-volt supply, other vehicle systems, and the car-specific CAN bus, though we might add a user interface with its associated low-voltage supplies. Simpler, eh? You might imagine that something like an unmanned drone might be simpler yet. Let's talk a little bit about the business side. I admit, I'm not an expert on this, but I know enough for a few slides. Plus, I have web search skills. Okay, I don't use Alta Vista anymore, but I did when it first came out. Battery cost is falling. Plotted here are lithium-ion battery cost estimates from 3 different sources. The exact numbers aren't identical, but the trend is a dramatic decrease. Can you think of another product or raw material whose price has fallen by a factor of 10 in the last decade? If you look further back in time, the effect is even more dramatic. The news has reported on an increase in price in 2022, but as you can see, that is a small blip in the overall downward trend. If you like this sort of analysis, I encourage you to take a look at the Ziegler paper, which has some really nice figures. Also, note that the true cost is secret. True cost is embedded in confidential agreements between cell manufacturers and their customers. Several things are driving these price decreases. Among them, energy density in watt-hours per kilogram has been improving over time, with engineering optimizations to cell chemistry. Cell materials engineering is an active and exciting field. You can see how many different cell chemistries are mentioned in this legend, and even that is a simplification. There is active research on cell cathodes, cell anodes, the electrolyte, the separators. Calling a cell NMC or NCA is really quite a simplification for so many degrees of freedom. Also, when you make more of something, you can make it cheaper. The plot on the right shows global cell supply and demand over time. We're making a lot more cells today than we were 10 years ago, and thus we can dedicate more engineering effort to manufacturing optimizations and invest in fancier equipment that manufactures better and faster. This data is from a report from Citi Research Group, published in early 2021. If you'd like to go deeper, Ziegler has more detailed analysis, but only up to 2018. As battery prices have been dropping, electric car range has been increasing. This figure is from Citi, a huge financial institution. The y-axis shows range in miles for a number of electric cars. The x-axis is time. The message of this figure is that vehicle range has been steadily increasing. What's missing is my past employer. In 2012, the Model S entered production with roughly triple the range of its competitors then on the market. As I see it, Tesla forced a step change in expectations for EV range, and this plot shows other manufacturers chasing Tesla. It seems like I have a Tesla bias, and Citi has an anti-Tesla bias. When looking at market data, keep the author's bias in mind. The last price-related topic that we'll address is LFP versus NMC cost. The predominant opinion seems to be that LFP is less expensive than NMC because of the underlying costs of the cathode materials. Iron and phosphate cost less than nickel, manganese, and cobalt. You can see that in tables like these from zecar.com and from the Pacific Northwest National Laboratory. The other view is that NMC costs less because it is more common and thus benefits from economies of scale. So I went to Alibaba.com, a website selling all sorts of things from China. I searched for LFP lithium battery or NMC lithium battery and noted down the cost for the first 10 or 11 results for prismatic cells. Prismatic, which is to say cells packaged in rectilinear boxes without any added electronics. And what I see here, on Alibaba, NMC cells are less expensive than LFP. State estimation is a topic worthy of its own semester-long course. I have a whole lecture on it, and what we'll see now is just a taste, just 2 slides. A BMS must measure cell voltages. It likely also measures cell temperatures and battery current. These feed into the state of charge estimation. To some people, state of charge estimation is the core BMS algorithm, and state of charge estimation is indeed important and requires substantial work to do well. But I would argue that for large batteries, such as in electric cars and in home batteries to supplement solar, safety is an equally important and complex topic. The BMS may implement additional diagnostic measurements to support fault detection and safety. Balancing is a small function in terms of current and complexity, yet essential. The state of charge estimate and some of the baseline measurements may feed into 2 other state estimates, namely state of health and available power. Power estimation directs the charger as to the maximum allowed charge rate and directs the motor or inverter or other load as to how much current they may draw. Battery switch control is a relatively straightforward yet important function. Let's take a look at the gist of state of charge estimation. State of charge can be expressed in percent or in units of charge such as amp hours. Conceptually, we have 2 ways to estimate state of charge. First, we can simply integrate the current. We know how many amps are flowing through our battery current sensor, and we can integrate those amps over time to get amp hours. The trouble with this method is that offset error accumulates without bound, so we need to supplement current integration with a reset to ground truth, either periodically or continuously. A second method is to use cell voltage measurements. The open circuit voltage of a cell is directly related to its state of charge, though that relationship is also a function of temperature. We can wait for a time when the pack is well rested, when the measurable cell voltage closely approximates the open circuit voltage. We can use the rested cell voltage measurement, along with the cell temperature measurement, to get the state of charge from a lookup table that we've pre-populated with cell characterization data. More sophisticated algorithms combine these 2 methods. That's all I'll say now, and if you'd like to know more, watch my lecture on algorithms. To put this in more intuitive terms, consider charging a battery to be like filling a vessel. Estimation by current integration is analogous to measuring the flow rate, measuring the time, and calculating the total poured. If we pour at 25 milliliters per second for 5 seconds, we've added 125 milliliters to the vessel. Estimation by voltage is like looking at the lines on a measuring cup. Measure the depth and look up the correspondence between depth and vessel volume. And this completes the introductory lecture in my Battery Management Systems course. If you liked what you saw and would like to see more, please let me know.